One thing that's wonderful about science is that it's not dead, it keeps moving. So, in the first version of this course many years ago, I assumed that symmetry is, obvious. Everybody knows about symmetry. There's nothing to learn. Totally straightforward. And now it turns out, when we look at more difficult problems like turbulence in fluid dynamics, we are realizing that symmetry is very, very important. And so far, it's been kind of a nuisance. I made you learn stuff. I don't know whether anything stuck, but I made you learn things that you didn't know whether you really wanted to learn. Cutting up discrete domains into slices of pie, of pizza. Slicing the continuous symmetries and God knows what. But now I want to convince you it was all worth it. Symmetry is your friend. Unfortunately, it's a very high maintenance friend. This friendship doesn't come cheap. That's why 5 lectures. So we are back to another idea. Now this idea is standard, it's not as original. Your professor knows this idea. What we have done in our transformation from studying short-time behavior to infinite-time behavior, in going from Newton to its dual representation in terms of evolution operators, we have reformulated the problem as a linear problem. So now we are looking at densities. And there is a linear operator. Linear. And even though this is course on nonlinear dynamics, we get the help from wherever we can. And linear things are incredibly well developed and powerful. In particular, if you have a symmetry, so there is this group of symmetries, and your dynamics, which is now encoded in evolution operator, if that commutes, that implies that we can use theory of linear representations of symmetry groups to block diagonalize our evolution operator. Bring it to the form in which most entries are 0. So there is a part which survives, but then everybody else is 0. And as we are interested in spectra, we are looking at determinants. And what symmetry does, whenever you have a determinant of an operator, linear operator that commutes with a symmetry, it writes it as a product of irreducible representation, also called irreps. And each one is much smaller. It belongs to one of these blocks. Each one is much easier to compute. It converges much better every calculation. Dynamics on the spaces that act, the vector space that you started with, function space, now is a sum of irreducible representations. They don't mix. So if you start with something that's, let's say, an anti-symmetric subspace, evolution will keep it that way. So you will never decay to natural measure if you're not in the right subspace. Things become very powerful. What we will do is we'll try to convince you that they're really powerful in 3 steps. First, I'll teach you translations. Then I'll teach you finite rotations. and then I'll teach you continuous rotations. And the first example that we have has potentially experimental behavior. So what we'll do, we'll study a world like looks like graphene, let's say. Plane covered with hexagonal lattice. And symmetry reduction replaces this by a small space, finite, this is infinite cover of the world, in which this edge is identified with this edge is identified with this edge, and this edge is identified with this edge. So it's some kind of torus, and that's called elementary cell. Finite rotations we actually discussed a lot. So if we had a pizza and we wanted to share it between 3 friends, and it had some kind of decorations like that on it. So if you rotated it was symmetric, but if you flipped it wasn't. That gets replaced by fundamental domain. And if we had rotation symmetry, suppose we were on a planet which was perfectly spherical, it had rotation axis, everything looked the same this way, but it had interesting features going inside or going toward the poles. What we can do is we can just take a slice of that. And what happened in these cases, we started with some big space, made it smaller, like by 1/3. But here we actually, when we look at this slice, we go from, let's say, 3 dimensions to 2 dimensions. We actually lose a whole dimensionality here. And then we can go back and forth. That's called reconstruction equation. If you know the group that brings us someplace, so it's plus the group. Same thing here. If you know the operation that brings it someplace in here, or if you know the translation that brings it someplace in there, then these are equivalent representations. But we will show that everything can be done on this small space, and all the computations of this linear theory are much more efficiently done on a reduced space. So that'll be my goal for next week. And again, it's one of these things, unless you actually do it, you don't appreciate it, because I have a table in the book in which my students and me compute escape rate from 3 disks. If I don't use a symmetry, if I use zeta function, and if I use Fredholm determinant. And if I don't use the symmetry for same amount of work, same number of periodic orbits, I get 4 digits. If I use the symmetry, I get something like 60 digits, and we have a 200. Same amount of work. Just thinking exactly. Because it turns out when you actually do this, this is much more powerful than statistical mechanics often, in the sense that if you go 1 step more in time, get more cycles, the error will decrease like e to the time square. So it won't be exponential, it's super exponential. That means the number of digits doubles every time you do a little more work of accurate digits.